Moving forward, I'm sitting here in Mumbai. It's usually very warm, not so bad, but I leave the windows open because I don't want to use air conditioning and so on. But now I have a strong breeze because I am on a lake. Maybe I can show you a little bit. So here I am. This brings a lot of breeze, and I see that there is a lot of sometimes hissing sound in the recording, so if it's too bad you can let me know. Moving forward on the models, how do we evaluate the models? There are many quantitative ways to do it, but we will just run through some simple qualitative looks to see what typically are looked at. So in general, it is known that the models have a much better skill of simulating temperature than precipitation, for example. Here is a comparison of the performance of a climate model considering atmospheric water vapor content at 400 hectopascal, which is somewhere in the middle, around 7 kilometer height, given as relative humidity in percent on a day in May. So in general, you don't look at climate models at such high frequencies. Weather models do that. In climate models, typically you look at lower frequencies, but nonetheless they have to be able to reproduce daily values in order to be able to produce realistic seasonal values, right? So the model simulation with the model MPI of model of MPI Hamburg at high resolution. So this is relative T106. So the models, I said they are split into grids, but as you can imagine, trying to fit grids into a sphere can be a problem. So often they are represented by what are called spectral representation. So how many waves can you fit to a sphere? So T106 is representative of that, which can be converted into a resolution as well. So when you see numbers like T106 or T387, 1500 something, it just means that more and more waves are being allowed to exist, which means smaller and smaller scales of the waves are being captured. So here is the mean relative humidity between 250 and 600 hectopascal based on satellite data, while uncertainties outside 30 south and 30 north are larger. So dry regions can be identified as white areas. So cold temperatures. Here is dry subtropical gyre. Cold in May. The evaporation on Arabian Sea is high, so water vapor is being advected over to India, so you can see high water vapor relative humidity here as opposed to here. So in general, you look at broad patterns and say the model is not doing so bad, even though you can see that here the data says relative humidity is in the range of 10 to 20%, whereas here it's in the range of less than 10%. So in general, broad contrasts are realistically captured by the model. So that's a very qualitative statement. To look at more realistically, here is the zonal mean surface air temperature for December, January, February. This is more like a climate model where we look at seasonal means, and these are different models with the thick black line representing the observations. What do you look here? So December to February temperatures in Kelvin zonally averaged for 15. So you expect warm tropics and cold higher latitudes, and there is a symmetry in the hemispheres. Nonetheless, you can see that most models are doing reasonably well, but there is a large uncertainty here because of the Southern Ocean being such a special place and models not doing so well, and the disagreement between models themselves themselves and from the observation is seriously large here. So the observed temperatures are estimated at under 250 Kelvin, maybe around 245 Kelvin, but some model like this one from Kola is at 265 Kelvin. So that's a massive difference, and the differences among models is also quite large. So in general, there are reasons why the southern hemisphere is more difficult for models than the northern hemisphere, because a lot of the parameterizations that are done often are based on northern hemisphere data. Southern hemisphere has much more ocean, much less land, and that plays into various biases, clouds and winds and so on. But you can see that one model here is also doing crazy things. The IMD model, I think, in the northern polar region, where instead of the observed 240 Kelvin, it's at 264 Kelvin or so. So again, model uncertainty or model differences from observations and among themselves is much higher here than in the lower latitudes and generally in the northern hemisphere. Here almost all of them are warm, whereas here they are on either side, warmer and colder. So these are kind of things that are used to understand models and intermodal differences. Another example, annual mean zonally averaged precipitation amount simulated by 23 comprehensive coupled climate models used in IPCC AR5, the assessment report, no sorry, AR4, I think assessment report 4. Observed estimates are shown by the black lines, bold lines, and they are compared with the multi-model mean in the black dashed line. So again, the point I made before, that the multi-model ensembles tend to be more realistic. You can see that the errors, the spread is averaged out, and we are closer to observations, at least in some places. But again, southern hemisphere problem here is consistent with what we saw here in terms of temperature. In general, I said temperature skill is higher for model simulations and predictions because energy balance and thermodynamics and heat is done better. Converting that into precipitation is very difficult for models because those convective processes, cloud processes and so on are not very well represented because of lack of understanding, plus lack of the representation of range of scales that happen in cloud formation, rain formation and so on. So there are parameterizations used to represent clouds and precipitation processes which depend on observations, and observations tend to be specific to regions. So land precipitation will be different than ocean precipitation, tropical precipitation will be different than mid-latitude precipitation, orographic precipitation will be different than flatland precipitation, and orographies are not well represented in the models because of the coarse resolution and so on and so on and so on. Also the decorrelation scales. So if you take temperature at one location and correlate it with temperatures around it, it will have a correlation over a large scale, whereas rain is like popcorn. Convection happens on small scales, so models have a hard time capturing those as well. But large scale features like the high rainfall band here in the northern hemisphere, which is the intertropical convergence zone that we mentioned before, and the mid-latitude peak in rainfall in the storm tracks in both hemispheres are reasonably captured, although the differences here are larger. And the model also has the southern ITCZ, which we will look at. There are specific biases here, and there are many studies that look at the biases here and see whether that bias is related to this or whether the bias here is related to the bias there and so on. So these tend to be very difficult because when you have a coupled model, error in one part can propagate into other parts, so it's not always easy to separate the chicken and the egg. So that's a very, very tricky problem as well. Here is an example of a very high disagreement between models. December-February cloud cover in percent zonally averaged for 10 AGCMs and its comparison to the observed climatology. And this is even a simpler way of comparing because there are low clouds, high clouds, deep clouds, rain-bearing clouds, and so on and so forth. So we are just averaging everything and looking at observations and looking at various models. So obviously there are difficult questions. If clouds are so different and rainfalls are so close to each other, what does it actually mean? So it has implications for how energy balance is done in the models, how rain is done in the models, how water vapor transport, moisture transport is done, and so on and so forth. We won't go into details, but as I said before, models are remarkably good. They are very useful. Given the energy at the top of the atmosphere, they are able to produce all kinds of features that we are looking at here. So one has to look at how many things they are doing well. For example, the Southern Ocean cloud bias here is very large, and there are questions about whether that is related to how there are biases in these regions or whether they are independent of that, and so on. Because remember, we are constantly trying to move energy from low latitudes to high latitudes, so precipitation and clouds are part of those processes. So if you have such large differences between models and differences of models from observations, then one has to obviously worry about that a lot. Keeping that in mind, now we look at annual mean precipitation from observational estimates. Even from observations, estimating precipitation is a very difficult task. These are typically done from satellites, and measuring a signal from Earth high in the atmosphere where the satellite is sitting, and then translating that into precipitation estimates is not an easy task. So even though we call these observations, there are lots of details that go into producing these observations. But nonetheless, in the annual mean, you can see the ITCZ clearly defined. There is the South Pacific Convergence Zone, or the SPCZ, and there is a version of the South Atlantic Convergence Zone here as well. In the Indian Ocean is a special situation because the ocean is warm, so the ITCZ remains, but you also get the monsoonal precipitation, and you get the mid-latitude storms here, clearly showing the secondary maxima in rain. You see the observations at first look, you think that's great, it's doing pretty well, but you look at the details, there is a dry bias here. Rainfall is much lower than in observations. These are also much drier than in observations, and this feature, which is tilting southeastward here very significantly, is made much more zonal in the model here, and it's southward and less intense here as well, and the Amazon rainfall is shifted and weaker, and so on. So these things matter. So for example, having an ITCZ that is much more zonal, which is known as the double ITCZ problem, affects the winds, the ocean circulation, El Nino, the heat balance in the ocean, and hence El Nino's impact on the monsoon and elsewhere, and so on and so forth. But again, it's amazing that the model is able to do such a realistic representation of the precipitation distribution, because there is also evaporation that is being done right to get the precipitation. So to generate such large-scale narrow band of rain by taking evaporated water vapor from the subtropical gyres, converging it, and producing the storm tracks means the energy transport is being done fairly realistically as well, and so on. And you can see that by, of course, looking at temperatures of the cold poles, warm tropics, and so on and so forth. So you can think of it as a car that runs great but pulls a little to the right, so you have to be careful with the steering to keep it going straight. But the climate scientists, climate modelers work relentlessly, tirelessly on improving the models, understanding the biases, and so on. So we will look at that in terms of the CMIP 6 and CMIP 5 models and compare them to show that these models are constantly being compared, and each generation they are being looked for in terms of what biases didn't get reduced and what biases did get improved, and whether whether those improvements are related to adding more sophistication like dynamic vegetation, land ice, etc., or are they related to increased resolution, improved chemistry, and so on and so forth. So it's a tough challenge, but we are up to it and we keep improving the models, right? So we'll come back and look at some of the CMIP 5 versus CMIP 6 models, and I haven't defined what CMIP 5 and CMIP 6 are yet. We talked about it in the earlier part of the course, so we'll look at that again to see what are the details in the models that we look for.